Now that we've walked through our end-all be-all implementation of a timed memoizer, TimedMemoizerEx, let's go ahead and take a look at how we can apply TimedMemoizerEx to our PrimeChecker app. And you can see here that this is the same app we've been talking about before. And this particular app is the one that checks if n random numbers are prime or not. Just a quick recap. You probably remember this from previous lessons, but this particular app, this PrimeChecker app, is embarrassingly parallel, and it's also compute bound. The main activity checks the primality of count random numbers using the executor completion service with a thread pool and this thing called a prime callable. In this particular case, just for the heck of it, just for kicks, we're going to use a work stealing fork join thread pool instead of using a cache thread pool or a fixed thread pool. And as you may recall from our discussions about how the fork join pool stuff works, it uses this work stealing mechanism where if there's threads that aren't being used, then if they don't have anything in their decks to do work with, they will go ahead and take their implementation. They'll steal work from somebody else's deck. The main activity also uses this TimedMemoizerEx to scalably optimize primality checking for the random numbers. So that's all the stuff we just talked about in previous lessons. Prime callable, basically the same as before. It implements the callable interface, and it keeps track of the prime candidate and the PrimeChecker function. And those are passed in as a parameter. And then the call hook method, which runs in a thread in the thread pool, the fork join pool, will call the apply method on the PrimeChecker function to compute whether a number is prime. And this particular method will be optimized transparently using the TimedMemoizerEx because that implements the function interface. What you get back here is this prime result tuple that matches the prime number candidate with the result of checking for primality. Here's the main program. We create a TimedMemoizerEx, which is going to encapsulate the prime number checker, which in this case is the brute force checker, but we could easily do a more efficient implementation if we chose. And we give a timeout, which is the number of elements times 500. So that'll basically be the number of elements times half a second. So if we have 1,000 elements, that'll give you, the 1,000 elements, it'll give you the number of seconds to wait to decide when to check whether something is stale or not, or when everything is stale. We then go ahead and create a stream of count random numbers within a range designed to induce duplicates. We convert each of those random numbers into a prime callable, passing in the number and the TimedMemoizer as the function. And this is possible because we have the TimedMemoizer is a function, so we can register it with something that expects a function, and then it transparently does the caching optimization that the memoizer provides with timer ability to purge stale entries. And then we go ahead and we use the for each method to submit each of these prime callables, and they get run in the fork join pool in the background and produce the results. Because we're using the executor completion service, there's just no need to have a list of these things that we handle explicitly. Instead, those are handled implicitly by the underlying completion queue that's part of the executor completion service. We create a thread that runs in the background that waits for all these things to finish. To do that, we make a runnable, and we make a new thread that runs that runnable. We start the thread, and then that thread's runnable is going to have a run method that will iterate through all the results and then call take on the executor completion queue, which could block until there's a result. And then we call get to get the result. And then we go ahead and print the results. Because we're running on Android, we have to deal with what happens when a phone rotates. So we have this retain state method that keeps track of rotations, and it stashes all the concurrent state so that things can continue running concurrently, even if the main activity is destroyed and recreated. So that's the end of the overview of applying TimedMemoizerEx. If you were to go back and take a look at the previous discussions, you'd see that they all have pretty much the same logic. It's just that we've now switched from using a timed memoizer to a TimedMemoizerEx. And we also tweaked for example, the type of thread pool, but the basic logic remains very similar.